Okay. Oh, there you are. There are. Hi. Hi. Can you hear me?
Yep, we can hear you.
Okay. Sorry, I somehow um I went to the wrong place. I think what happened was I didn't click start meeting on the right one, and somehow I went to the old meeting, and it somehow it regards this as a different one, even though it came from the same link on Moodle. So okay, I guess next time I'll know what to press. But anyway, we didn't lose much time, luckily. Okay, so of necessity, we are having this lab online. I don't know how long this will last because of the bad COVID going on. Both of our professional secretaries are now not on location. They're working remotely. That's an indication of how bad it is. Um, and so be it. We'll try our best, right? And let's learn something anyway, despite this problem with COVID, and hope we come out of it all right at the end. So uh, so our lab kits are not here, but we'll uh, take advantage of the situation anyway and learn more about simulation. And with simulation, uh, we can design circuits faster than wiring on the breadboard, where we learn um, other practical things. But anyway, so let's do that. Let's go the simulation route. And we've learned about how to make a 1-bit adder. Well, now it's time to make that into a multiple bit adder, something real that can actually be used. And yes, it's in simulation, but it does work. So let's do that. I wrote up a lab for you, and I'll supply you with the details, and then your job is to write that up, all the procedure. Okay. So let's start this. You can do it along with me. That that would actually be the best way to do. And if you have questions, feel free to interrupt. Uh, don't mind slowing the class down. I don't mind the class being slowed down by that. I think that's a great thing. So I hope you have LogiSim with you. And so all right, this is at home, so there are things happening. Like suddenly there's a cat fight out there, right outside here. Help that, but okay. All right, let's get LogiSim up. Okay. No, I don't know what happened to mine. Oops. Okay. 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 All right. So, all right. Now I can share LogiSim. I had to quit the program, otherwise it didn't work. So sorry about that. Let's go back to Zoom. Let's see. Okay. Now I can say share screen. Okay. LogiSim. Okay, now do you see my blank LogiSim screen?
Yeah.
Okay, great. Okay, so what I want you to do is start a 1-bit adder here, okay, the optimized one. Now, we're not going to just put it on the main circuit. You see, when you just open up LogiSim, what you have is called the main circuit. Okay. Instead of that, we're going to design this adder in a modular way. Now, you know, this program works extremely well. If you've tried other programs, including expensive professional ones, you know that this is really good. Superior, in fact, to a lot of the paid for ones out there, because it actually works. Sometimes some of those programs have so many bugs. Okay, so here's what you do. I want to design the circuit in a modular way. And the way you do that in this program is you say, create a circuit. Okay. And then you create a circuit with pins, which will act as your ports to the next level. It will be your ports so that when you design another circuit that uses this circuit, okay, you'll be able to see the ports. Get it? So let's do that. So instead of designing anything here, you start by saying project add circuit. And then it'll come up and say circuit name. Okay, you can either call it add one for 1-bit adder or FA for full adder or just full adder. I'm going to call mine full underscore adder. Okay, so now if you look on the left pane here, we have two circuits, main and full adder. And actually, we don't need main at all, but that's okay. Now, this full adder here, you see that's a magnifying glass symbol. Okay, you can change it by double clicking on a different circuit. Okay, so let's put the magnifying glass on the full adder, and it should be there already unless you moved it. So that means you're now looking at and editing the full adder. Well, can someone tell me how many 1-bit inputs a full adder has and how many 1-bit outputs?
Just 3 in, 2 out.
Yeah, 3 in and 2 out. 3 in are carry in, and then the 2 bits, which we normally call either XY or AB, whatever. Let's call them AB. So we'll get these ports, and the ports facing east, that means the wire faces east. That's the usual for an input pin, and it's not an output. The data bit is 1. Later on, you'll see ports with more than 1 data bit. 3-state, no. 3-state means you can have 1 or 0, and you can have high impedance, which means basically it's cut off, like an open circuit. Okay, but we don't need that for now. Pool behavior. This has to do with pull up behaviors, so we don't need that. So so we'll get 3 of these and we'll label them. So we'll do a label of C in. Make that 20 points, and X or A, whatever, not Z, A, 20 points, B, 20 points, oops, sorry, 20 points as well, okay? And now you can save it. Okay, so now, let's compute S for the sum. and C out. Okay. What is the circuit for the sum? Can someone tell me? It's the modular 2 sum, or exclusive OR with 3 inputs. You can say it's a cascade of two input exclusive OR gates, or you could make it a single 3 input exclusive OR gate, in which case you have to choose as its behavior that it will be a 1 if and only if an odd number of inputs are ones, right? So let's do that. Now, the exclusive OR gate is not on this bunch of tools up here. So you have to go to gates, okay? And you say exclusive OR, a number of inputs. Let's make that 3, right? And what is needed for an exclusive OR is you have to make a choice here. Multiple input behavior down here. When one input is on, instead you want to say when an odd number are on, meaning an odd number of inputs. That's what they mean. Okay, so I'll put that here, and then I'm going to run a wire. And the output, this rounded thing is the output port, see? So now I'll label.
Professor, could you show what you did to like get the exclusive OR gate again?
Okay, I will. Let me just label this, and then I'll do that. Yep. Okay. You see this panel here? It started out like this, right? This is all the gadgets you can have. Let's call it that way. Okay. And up here are your own circuits. Okay. So you have wiring gadgets, gates, plexers, which stands for multiplexers, demultiplexers, and some other circuits. We'll learn about them later. Okay. And arithmetic. You can get circuits that do arithmetic right here. Like instead of designing this, you could just say adder and you'll have it. But I don't want you to do that because I want you to design your own. Okay. But see, there are lots of different arithmetic circuits available, some of which I haven't even used. And then under memory, these are 1-bit memories, which are pretty cool. You'll learn about them later on. Okay? And these are bigger memories. Okay? There's even a random generator counter, which can count. We can try that this time. Okay. And then there are some certain input-output things. The pins, however, are inside wiring. Okay. But these are like LEDs. Your keyboard, that's a keyboard even. The big keyboard. Anyway. Joystick. Hexadecimal digit display. Okay. You can put 4 bits in, and then it'll, it gives you a hexadecimal display of those 4 bits. And then there's another input for the decimal point. Okay, it's pretty cool. Maybe hexadecimal point if you like. You could use whatever radix you want. and LED matrix. You can have a whole matrix, two-dimensional matrix of LEDs. And you can have a teletypewriter. Some of these I haven't used. Base means like basic things. Okay. Hope tool, like this one is there, basically for simulation. Edit tool, select tool, wiring tool, text, this thing, menu, label. Right? Some of these I haven't used. I have to say, could be fun to try, but for now, we want to concentrate on these circuits. So how do I get an exclusive OR gate? I expanded that, and then if I go down the list, I'll see exclusive OR. So that's how I get it. And it'll come up with a medium-sized 5-input model. So I changed that to 3. Okay. And then for output, instead of 0 or 1, I could have 0 floating and floating and 1, but I don't need those. And label, I can have a gate label. Say if we want, if we want to call it XOR 1, I could do that. See. But anyway, the important thing about that gate is this multiple input behavior. Okay, you have to make a choice whether to make the output 1 when all the inputs are 1, or to make it 1 when an odd. Sorry, you make it 1 when exactly 1 input is 1, or 1 when an odd number of inputs is 1. Like right now, it's choose to be 1 when an odd number of inputs is 1, right? Maybe I can make that the label, right? Odd number. Well, doesn't show very well, does it? What if I just say odd? Okay, so that we know that's what it does, right? See, if I have 2 of these equal to 1, and then the output is 0. If I have all of them high, then the output is high again. Whereas if I were to, let's see, if I were to choose this, you'd get a 0 here. Okay. Any more questions? Oh, I haven't saved this yet. So documents. Okay. Now for the carryout circuit. The carryout, whereas the sum circuit is the parity circuit, right? The carryout circuit is called the majority circuit because the output is the same as whatever the majority of bits in the 3 inputs are, right? So what's the Boolean expression for that, for the carryout circuit? Do you remember? Let's call C in C to make it easy. It's AB or AC or a BC, right? Basically, it has 3 AND gates at the first level, closer to the input, where each AND gate has 2 inputs, and there are three possible combinations of three inputs. So these three AND gates will take all possible combinations of two inputs, right? And then once you get the outputs from the AND gates, you gather them into an OR gate. And the output of the OR gate is then the carry out, right? So I'll get an AND gate. Again, it wants it to be 5. I'm going to do just 2 inputs. And I'm going to do this narrow, okay? So 1, 2, 3, okay? And I'm going to take the 3 different pairs of inputs and put them here, right? So let's see, you know, if I move. So let's do CA, right? A, B, right? This is C, A, B, right? And B, C, right? That should work, right? So let's see, C, A, B, and then B, C. Okay. Or I could run this from here, right? This is B, C, right? And you know, if I want to label these, this is CA, right? And this is A, B, right? And this is C, B, right? Okay, just to try to reduce the confusion. And now, confusion occurs easily, by the way. So now let's take the OR gate. So this, I want it to be 3 inputs. So that, right? And then C out. Make that 20 points. And then save. Okay. So now I want to test this, right? Now, when you test the circuit, one way to make the result easier to read is that you want the output bits to look natural in the sense that you want the sum bit, which is really the unit position, to be to the right, and then the C out bit to be to the left, right? So, I mean, you could move these pins, but pins shouldn't be moved around too much. It's good for pins to be either the left or the bottom, and outputs be on the right or the top. Okay? And if possible, maybe if all the pins are on the left, all the inputs on the left, all the outputs on the right, that would be nice. That would reduce the confusion to have the signal flowing in one direction from left to right. So you would put a probe or an LED in. So let's look at input output. An LED is basically a probe. Let's see what's in the base. The LED is the best kind of probe, maybe. So let's put an LED, 2 LEDs in that are facing south, meaning the wires are down, and then you put the C out to the left of the S. Like that, okay? So now you want to test this, right? Okay, save your work often. You take this poke symbol and you turn everything to 0. So when you have all the 3 inputs to 0, you're adding 3 zeros together, you should have a 0. So in 2-bit binary, 0 is 0, 0, see? And if you have a single 1 bit here, then you should have 0, 1, right? So single 1 bit, you have 0, 1, 0, 1, and another possible choice of a single 1 bit is at the A, 0, 1, and then at the C in, you have 0, 1 as well. Now, let's do 2 1 bits at a time. You should have, what will these read if you have 2 1s and a 0 in the input? If you have 2 1s in the output and a 0, sorry, not output, sorry, input. If you have 2 1s and a 0 in the input bit, what would this read out?
Yeah, it would light up and S would be black.
1 would be 1 0, right? If you have 2 1s and a 0 in the input bits, then the output bit should be 1 0, right? Because that's a 2, right? Does that make sense? Does that make sense?
Yeah, that makes sense.
Okay, great. You're adding 3 1s. So sorry, you're adding 2 1s and a 0. Okay, there you go. So you get a 2. Okay, and 2 is 1 0. So red, black. Okay. Now, what are the possible choices of 2 1s? You might as well make use of these gates and their labels. Because in case there's a mistake, then you'll know what's wrong, okay? So these labels and these gates represent all 3 possible ways of having exactly 2 1s, okay? So the top gate here is CA. So let's make C1 and A1. This should be light green. This should be 1, and it is. And the others should be dark green, and they are. So that's what you expect. And here, that is what you expect too. So in the case where the 2 1s are C and A, you're okay. C means C in, of course. So now the next case is the case where A and B are the ones that are 1. So A and B. That output should be light green, and it is. And that should be 1. that should be 0, 1, 0, correct? 1, 0 is 2, right? And the last case, the last pair of ones in the inputs is CB. So CB like that, right? And there you have that output light green and the others dark green, that's correct. And the outputs there should be red and black, 1, 0, right? So you're done there, except for the case where all the inputs are 1. So you test that. Then the outputs should be 1, 1, as expected. So this circuit works. Any questions? The other possible way of testing this circuit is to drive it with a counter. We'll look at that later. A counter is a circuit with memory. See, the combination of circuits has no memory, in the sense that the present output is dictated totally by the present input. But a counter is a circuit with memory, where the current or present output depends not only the present input, but also what the circuit was outputting before, or what the circuit was remembering before. We'll take a look at that later if you remind me, okay? But right now, we'll go ahead with designing the adder. Now, here's the next exciting thing. The next exciting thing is now to design the next module up using this circuit as a component, okay? Actually, several times. We'll use this 1-bit adder, 1-bit meaning 1-bit position, in the scheme of things in the adder. This is 1-bit position. Even though it has 3 bits of input, they're all, the units are all the 2s, or all the 4s, all the 8s, whatever, right? So we're going to make a 4-bit adder, a 4-bit position adder out of this. So what we're going to do is we're going to add another circuit. Sorry, the screen is a bit messed up. Okay, take a look at this. Now we have 2 circuits. Actually, you know what? We can get rid of this main, because there's nothing on it. So right now we have the 1 circuit, right? Which we're looking at is the full adder. Go now to the project menu and add another circuit, okay? And let's name the circuit here add 4 for a 4-bit adder. And as you can see, now we're looking at it. If you double click this, you'll be at your old circuit, right? Okay, now, now we're on the blank palette here for the 4-bit adder, right? Now I'm going to click this just like I click any gate or any tool, and that will bring our full adder here, okay? This black box, as they're called, because there's nothing known inside, this is representing our full adder. And you see these little nibs here. These are actually the ports, okay? And it's their convention to not put any lettering on there, but you can tell what each port represents by doing a mouse over. C in, A, B, F, C out. Now, this is kind of small, so you go down there, you see that it's showing at 133%. You can go, that's too big. You can go up, let's say to 200. Okay, and that will be bigger, but it will not show what's inside anyway. Okay. Now, my idea, okay, is to turn this 90 degrees counterclockwise. Actually, let's turn it clockwise because I see. I want to put the adder for the units on the rightmost position, and then the next one would be the adder for the 2s, and then the 4s and the 8s. Okay, and if I turn it, so see out is here. If I turn it clockwise, see out will be on the bottom left.
You know,
1 second.
I need to turn the air conditioner on. It's getting hot.
That's
So
fine.
It's gonna be a little loud. You
Yeah.
have to talk louder.
Yeah, that's fine. And my wife said she has to turn the air conditioner on because the house is heating up because of greenhouse effect from the sun, even though it's cool outside. So if you don't hear me well, please let me know and I'll talk louder. Okay,
Professor,
yeah.
I think I may have missed. How did you zoom in and make that bigger?
Okay, great. Look at the bottom left of your window, right? It will say 133% or something percent, right? Do you see that?
Yes.
Okay, and now if you go a little right of that, there's an up and a down arrow. You can manipulate that.
Oh, okay. I see him now. Yeah.
Or you can type a number. You can type a number. Oh, no, you can't. Sorry. Take that back. You can't type a number. You have to use these arrows, up or down. Okay. So now the next thing I want to do is select that again. When you select your adder, it will say facing. Okay. So instead of east, you just say facing south. Okay. You'll be rotating it clockwise. Okay. And that's what you want. And so now I'm going to put 4 of these. I can say copy and paste. You can use your keyboard shortcut for copy and paste, right? For Windows, it will be Control C and Control V. On the Mac, it will be Command C and Command V. I don't know if any of you use Linux or not, but I don't know what it will be. Probably like Windows. And actually, you have to say copy just once, and then you just say paste, paste, paste. But each time after you do a paste, you have to move it. Unfortunately, I don't think this thing would paste something where the mouse is. I think it just pastes right next to the thing. It copies, and then you have to use a mouse drag to move it. Okay, so you have 4 of these. Okay, let's move it right a little. Okay. Now again, you'll want at each level, you'll want the inputs to be on the left, or left and bottom, and the outputs to be the right or right and top. It's not necessary, but it makes it nice that way. And you want to space these equally. I'm not spacing them very equally, but I guess that's all right. Okay, equally enough at least for things to not be hard to read. Okay, so now what I want to do is I want to connect. You see, if you mouse over, you know that's the C out part. You want to connect the C out to the C, and that's the C in. Now, note that the 3 inputs are symmetrical. If you remember that from when we designed the adder, it doesn't matter which of the 3 inputs you label C in or A or B, right? But in terms of documentation, it still makes sense to use the C in port as the carry in to each 1-bit adder instead of using the A or the B. So I'll put the C out of this rightmost one into the next one here. And this one, I'm going to label it the adder for position 0, right? So I'm going to label that unit 0. One. Although, let's see. You know what? Label location. I'm going to say, I can't say middle, can I? Oh. I don't have any shared label. Okay. Okay, so I now have all my adders. You can call them adder instead of unit. You could call them add 0, add 1, whatever. Whatever you want. Okay. So this goes like this. Okay. Okay. So now what do we do? Now you need to be able to put some inputs in. First of all, there's a carry in to position 0, right? Let's deal with that later. Let's look at the A and the B. That's the A and that's the B. You can switch A and B, it doesn't matter, but for documentation purposes, it makes sense to stick with what we have in here. A is the one to the right and B is the one to the left, right? So now we want to add the pins for the A and the B, right? So we take the input pin, right? And we add A, but you really want this to have 4 data bits, okay? Instead of just 1, okay? And if you run a wire out here, this will actually have 4 bits, okay? So now, watch this. I want to split this wire into 4 different wires in order to be able to put those individual bits into these adder units. So I'm using a splitter, okay? And right now the splitter is facing east. If you look at this figure, this funny claw-like thing, at this bottom left end, you really have 4 wires, or many wires, let's say, going in, and then on the right hand side, on the east end, it's the split end. Okay, so first of all, you want the split end to face down. So you say facing south. Okay. Okay, let's put it down. And as you can see, right now, the width of the bit that's going in is 2 bits. Okay, and so this end of it is 2 bits, and then the fan out is 2. The fan out means the split end is split into 2 different paths. You don't want that. You want the bit width in to be 4 because you have 4 bits going in. Okay. Now the fan out, you want 4 also. Right now the fan out is still 2, and you may be able to see here. It says 0 to 1 here. So the right branch is actually 2 wires. The 0 means like rightmost, and the next one, and then 2 to 3, the 2 leftmost bits are going out on the right, on the left end. So instead of 2 here, you change that to 4, and as you can see, the rightmost bit, the rightmost bit here, which is called the 0 bit, is going out here. The bit number 1 is here, and the bit number 2 is here, and bit number 3 is there. Okay, so that's correct.
Professor,
Yeah.
how did you get like the little black box with like 4 zeros in it?
Ah, okay. This thing, right? Okay.
Yeah.
Okay. Here's how I do it. Go to the pin there, right? Or wiring pin, either one. Okay. You get a pin. Okay. By default, the pin is made for 1 bit data. Okay, but you want that to be a 4-bit pin instead. So there you go. That's all I did. And then I use the mouse to wire it. Got it?
Yeah, I got it. Thank you.
Okay.
So mine has a bunch of X's in it, not zeros. Did I forget to do something?
Oh, that's okay. Let's check your settings.
Oh wait, I moved it around and it turned to zeros.
Okay. All right then. I'm going to retain this one that I did as a demo for you because I need one for the B's. So this is for the A's. I'm going to label it A. On this one, I'm going to label it B, okay? And I might have to move these around a little bit, but for now, that's okay. So that's okay. So let's check something. These are dark green, representing all zeros, okay? Now, if I were, let's save it. So if I were to use the hand symbol for simulation, poke tool, right? If I make that a 1, you see that becomes light green, right? And if I make this a 1, you see that? So I'm able to change that, right? Now, what I'm going to do is I'm going to put that into the A port. The A port is the right one. So this is the right hand one, right? The A port. But I want to minimize wires going horizontally. So one thing I could do that is I could move that all the way so that the that wire there is aligned with this one here. So I can just wire that vertically. Okay. So now I have a connection. Now I should wire. See, it's so easy to make the wires messy. So let's wire these horizontally like this first. Okay. And now I'm going to put that, pull that down here, that down here, and that down there. Okay. So that, see, by wiring these horizontally, I'm sort of reserving these 3 horizontal channels. I could even wire these further, even though I don't need these. But in case I do for any reason. Okay. So I'm sort of like reserving these 3 horizontal channels for the A's. And so I now know I need 3 more for the B's. There's hardly enough room. Let me move that down just to make things a little more spacious. You know, even though I don't really have to, just to make things easier to read, I'm going to see if I can move that. Okay. Okay. Now let's save that. Command S or Control S should do that. And now I'm going to need another one of these. So I'm just going to copy that. Pull that. Uh-oh. Okay. That's the danger of copying. Let's try again. Okay. Well, that's not so good. There's a line there. So, let's do something. Let's move everything right. Let's see if we can do it. Now, moving a whole bunch of things can be a little hard. You first kind of blacken it by clicking and dragging, and then you have to click the mouse somewhere inside. Oh, if those things disappear, it doesn't work. No. It's hard. Let's see. No. Hmm. Somehow I lost the art of moving I was just doing it. Wasn't I? Come on. Hmm. Well, I got it. Whoops. No, a little too far. No, that's terrible. Okay. Let's see. If you blacken things and then you press on one of the corner uh, the squares that are on the outside, and then, oh, come on. Let's see, just press on one. And if everything grays out, why did it work before? If everything grays out, then you can move it. And I don't quite understand why it worked that time. Let me see if I can do it again, okay? Okay, I select it. And if I click on it grays, then I can move it. But if I click and it doesn't gray, then it doesn't work. See, and I'm not sure, like if I click on here, it grays. If I click on here, it doesn't gray. This works too. If I click on it and it makes a circle, then it won't gray. How about that? But if it makes a circle, it won't gray. But if it like here, it doesn't make a circle, right? So it will gray for me and I can move it. So maybe that's the rule. If you click on, if you select a whole bunch of stuff, you see all these rectangular boxes. If you click on one that doesn't gray, see if you mouse over and there's a circle, you can't use it. But if you mouse over it and there's no circle, then you can click on it lightly and it'll gray. If it grays, then you can move it like that. Hopefully that will always work. Okay. Anyway, though, I moved that to the right so that I can move this thing here. Okay. And yeah, that means it takes a little room. So I'll move that. I'll connect that to this. And I'll connect this to this, right? And then I'll connect this to that. And I'll connect this to this. Okay. So now you could put numbers in there and see what happens by looking at the colors of those nips, but they're hard to read. So a better thing would be, first of all, you need to input something here. So that's your C in, okay? So let's put this in here. And this is your C in. Okay, but let's call it C in 0, okay? Because it's the 0th bit that you're carrying into, okay? So now that's Cn 0. Now, for the output, you're going to have an S that has 4 bits and a C out 3, right? So so you have a rounded 4-bit output labeled S, 20 points. And that will be here, okay? X means you don't know what's in it, because it's just a pin. It hasn't been driven. It's an output pin. So what you do is, where you see these S outputs here. So you want to wire this into that. To do that, you're going to need a splitter again. So this splitter is again same thing. The fan out is 4. Actually, truthfully, it's a fan in of 4 and a fan out of 1, but they call it the opposite way because they use the same kind of splitter for the output as they did for the input, as they do for the input. Okay. So let's rotate that instead of south, it's facing north. Okay. So now I'm going to wire this to that, right? And now I have 3 more bits, right? All right. Now I have this carry out. See, carry out output. You just want a 1-bit output here. And the label is C out 3, right? The carry out of the 3rd position, unit 3. And I'm going to make this, sorry, a little smaller. Okay. Save. So now you can add whatever you want. You know, but 0 plus 0 is 0, right? And if you have a 1 carry input with no non-zero A or B inputs, right? You should get a 1 here. Sorry, a 1 at the S. You should get a 1 at the S. So you do, right? So let's put that at 0 again. So let's say 1 plus 1, you should get a 2 here, right? So 1 plus 1 gets you a 2, right? Well, if the carry in is 0, how big does A plus B have to be for that to be a carry out? What does the sum of A and B have to be? For the carry out right here to be 1. What's the maximum number you could represent with 4 bits here in the S? Well, if you have 4 bits, what's the biggest binary number that you could represent in the unsigned world, at least, with 4 bits? Well, the number is whatever 1111 represents, right? What does 1111 represent?
It's gonna be noisy because the reason she keeps squawking is she wants me to change the water.
Oh, okay.
So she'll get super noisy for a couple minutes.
Okay.
Then I think she'll be better once I change her water.
Okay. Okay. Let's count up in binary. And so 7 is 0111, right? So 8, what's 8? Eight is 1 followed by 3 zeros, right? That's 8, right? Now, 9, what's 9?
One zero zero one.
9 is 1001, right? And 10, 10 is 1010, right? 11, 1011, 12 is 1100, 13 is 1101, 14 is 1110, 15 is all ones. So all ones is 15, okay? We can test that by let's add 7 and 8, right? That should give you 15, right? So 7 and 8, and that gives you 15, right? Now, if you were to add 7 and 9, you see, that's when you get a carry out of 1 followed by all zeros. Because 1, this is like the 6, it's like the bit position that's to the left of these 4 positions, right? That's the 16th, right? So one of the 16s is 16, right? So 1 followed by all zeros gives you 16, right? Now, if you add 1 more to that, that is instead of 9 here, if you have a 10, then you have 17, right? So on and so forth. So anyway, this works as an adder of 4 places. You can test it with more digits. So one of the things you have to do for the lab is once you have this circuit, you test it on several pairs of numbers to see if it works right. Okay. So there's your 4-bit adder, add 4. Okay. So now you can go back and look at the full adder, or you can look at add 4. Okay. Any questions?
I'm still having the problem where everything appears as an X.
Everything appears what?
As an X on the
Oh, as an
input.
X. In the input? Okay.
Yeah.
Let's take a look at your, let's take a look at, click on the arrow here, right? On the tool selection, and click on one of those pins. Okay. Do you get access?
Yeah.
You're getting access? Okay. Let's check a few values here. Is there any of these values that's different from what I'm showing here?
Oh, I didn't realize the output had to be set to no.
Ah, there you go. Yeah. You have an output pin there, that's why it says X. Now, output pins don't have memory for this particular setup. So if you have nothing driving an output pin, it will say X. Okay. Okay, so now is everything correct? All the input pins should say no for the output.
Yeah, I think it's working now.
Okay. On the other hand, on the output side, all the output pins have to say output. And on the 3-state, it should say no. All right, so oh, wait a minute. For the output, the 3-state can say either yes or no. It doesn't really matter. Okay, on the output pins, but on the input pins, it has to say no for 3-state. Okay, so there's your 4-bit adder, add 4. Now let's add another circuit. Project add circuit. So this is your add 16. This is your 16-bit adder. Okay. You're gonna set it as main circuit. Although you don't have to say that, it'll work anyway. But if you say it, then at least if you open up the file, that's what's gonna show up. So add 16 right now is a blank slate, of course. So now what you want to do is you want to add 4 4-bit adders on here.
So I don't think my add 4 circuit is like working. Like I'm not getting like any output.
Oh, it's not working? Okay, well, let's take a look at it. I'm getting it back. Okay, so where is it not working? Describe it to me.
It's not. I'm not getting like anything. Like
Oh, yeah, maybe
yes, like
maybe you should show your. I should let you show your screen. Could you tell me who you are?
it's noble. No.
Nova. Oh yeah, okay. I can see a green thing around your name here. Okay, let me figure out how to do that.
So I think you have to stop sharing your screen before somebody else can.
Right, but I have to first let him share his screen first. Let's see where that's settings. 1 second. Oops. I don't know. Let's see. Oops. 1 second. I don't know why. Let me see. Somehow I don't see Noble anymore. Let me. 1 second. Something happened. Oh, right here. Okay. Let's see. Make call. I guess one way, the way I do it, the way I allow you to share things to make you a co-host. I don't know if that's necessary. If you know something better, let me know. but the way I know how to make him share screens to make him a co-host. And I have to stop sharing. You're right about that part. Stop sharing. Now he can share. You can share your screen now, Noble. You know how to do that, right? Okay, great. Okay. Now you said something's not working. What's not working?
Yeah, wanna like do the first example that you did, like there's
Ah.
nothing.
Oh, I see. You don't get the right output.
Yeah.
Okay.
I don't think he has his S set to output.
Oh. Yes, you're right. Good job. Ah, there you go. Thanks for noticing that. So now it does output. No, wait. The result is still not right. 1, 2. No. You get a 2 instead of 3. Well, at least it's progress. At least it's outputting something different, but it's still not right. You get a 2 in the output instead of a 3. Well, if someone else sees something, let us know.
In the settings for S, if it says output question mark, you click yes.
And X is now.
Oh, now it's all X's.
Try like picking it up and moving it around. That fixed it for me.
Oh, wait a minute. If you look at the colors of the wires coming out of the unit 0 and unit 1, they're correct. But somehow they just don't go onto the export correctly. Why don't you click on the the splitter? The splitter down there. The
Which one?
splitter, yep, that one. Click on that. Let's examine that. Why don't you jiggle that, move that around a little bit? Okay. It seems okay.
I think he has the input for S facing the wrong way as well.
Oh, is that it?
Where's
I
the
think you're
face?
right. I think you're right. It should be west.
West.
I think you got it. Okay, and now you can connect. There you go. Very good. Thank you.
Nice.
Thank you.
Thank you.
All right. So I think that's it. Okay. All right. Seems like your problem might be solved, Noble. Thank
Yeah,
you.
thank you.
Yeah.
That is scary stuff.
to 8-bit and so on.
And so, so now we are going to scale it up to 16 bits, right? Uh, and we're going to do it again in a modular fashion. Imagine if you were to do a 16-bit adder, if you were to do a 4-bit adder without using the 1-bit adders, it would be a lot of gates you have to connect. And if you're going to do 16-bit adders without using any modules, it would be even worse. Now, you could do a 16-bit adder using 1-bit adders, but that would still be a lot of wiring. But if you do a 16-bit adder using 4-bit adders, that's a lot better. And you also know that each 4-bit adder has been tested, right? So now let's do that. The process is the same, going from 4 to 16 as going from 1 to 4. The only difference is now the splitter is a little trickier because you're not splitting a big bus. A bus is a bunch of wires. You're not splitting a bus into strands of single wires, but instead you're splitting a bus into strands of 4 wires. But you've seen 4 being split into 2 already, in the as we are trying to split 4 into 1s. So it's basically the same principle. So let's try that. So let's look at add 16 now. Any more questions though about the 4-bit adder? Did anyone have any more questions? I think we all got it. Okay. So let's try 16-bit adder. So let's lay down some 4-bit.
You're no longer sharing your screen, by the way.
Oh, I'm sorry. Let's re-show. Thank you for letting me know. Let's see. Where am I? What? Let's get my Zoom. Share screen. Okay. Oh, there you go. One second. Let's I need a different view. 1 second. Somehow okay, I got it. Okay, change this view. Okay, I got it. Okay, so that's an one second. Are you? I'm sharing. Yes, I'm sharing the screen. You're seeing this thing moving around, right?
Yeah.
Okay, great. So now I want to rotate this around again. I want to rotate it clockwise because I want to lay it down from left to right, from right to left like before. So they're facing east, I say face south. Okay. So 4 by 4 is 16, so I need 3 more of these. Oops, sorry. Oh. Okay, there you go. By the way, if you were to actually lay down 16 one-bit adders, it would be really wide too. This way it's much narrower and nicer, okay? 4 seems to be the right number for a group. You could group 2. Well, if you're making an 8-bit adder, then of course you'll be grouping 2 of them. But if you're making a 16-bit adder and you're gonna go 1, 2, 4, 8, 16, that would be too many levels and too few of them to a level, I think. Okay, 4 is just about comfortable, I think, my opinion at least. So I want to put this carry out, carry in. I'm not going to label these this time. If we find that necessary, we'll, well, let's do it like this first. If we need to label, then we will. So, okay. Now, I said the splitter is a little trickier, but not very different. So let's get an input here, right? So A. So now we're going to have to say data bit 16, right? Now, how do you work with this? Let's move that. The most significant bit is here, okay? So, so it goes bit 15, 14, 13, down to 9, down to 8, sorry, and then 7, 6, okay, down to that is the unit right down there, okay? Now, if you want to display that in hex, okay, you could do it. Okay? But we'll do that a little later. Let's split that. So you want to call get a splitter. Now this splitter, you're gonna get 16 lines in, right? Now let's make that bigger so you can see what I'm doing. Okay. The default is to split this into 2 equal pieces. 15 to 8, 15 down to 8, and 7 down to 0. But instead, I want to split it into 4 pieces. So instead of 2 here, I'm going to say 4. And it splits it nicely into 4 equal pieces. If you don't like it, if you don't like the pieces equal, or if you like the mapping different, you can fix it here. But since we do want it that way, that's okay. Now, this we're going to call this our A, let's say. Make that 32 points, okay? So let's call that A, and the A port is the right, it's to the right of the B port. So the A port so let's pull that over here. So that will be connected to here. If the number of lines coming out here is not right. It will change the color of that to a weird color. Let's try it. Let's say if you want to split that into two pieces, just say you, it'll not be right. Okay. So you want 4. It's okay, but that made the wrong connection. Oops. Okay. Okay. Now I want this to be connected to that. This to be connected to that. Okay. So that's your A. And then that connects correctly. It doesn't complain. When it complains, it'll be a weird color. Okay. So this is correct. Now I'll do another one for B. Oh, let's try to do a hexadecimal display for each one of these split things. Okay. So I see input output. Okay. Hex digit display, right? So if so that's the main display. I think, and that's, I think, is a decimal point. So if it connected to this, oops, sorry, I didn't. It should be this. So that displays 0. Let's see. If I put a 1 here, it show 1. See, 3. See, 7. See, 15 is F, right? 110 is D, right? Makes sense. So now I'll get more of these. These are nice. I'll get more of these. And this is this one. 1 second. This is wrong. I connected to the wrong place. This should be connected to that, and that should be connected to this. Okay. All right. So then I can, put whatever you need. Okay, so you have these showing in hexadecimal. I'll try to equalize the spacing some. Okay, any questions? Okay, so that's my A. I'm going to move this down a little bit so as to have a little more room. Oops. And now I'm going to have a B. I'm just going to copy this. And then change the label to B. Okay. And I'm going to copy this. Okay, I guess this will work. And this is my B part, right? So that's my B part. Now, I'm going to have to find room for a hex display for the B's too. Let's see. It's not going to be the easiest, but okay. So let's see if we can do this. Yeah, here's one of them. Here's the second. Maybe I'll move this out here. There, that's good enough, I guess. Okay. Wiring in real life is even harder than this. To find enough room to wire things, you have to kind of be very organized. It's really hard. Okay, so now I'm going to display this one. The next one goes like this. And the next one goes like this. Oh, that's good. It's almost done, right? And this one something's wrong. Oh, right here. So this should be that unit. No. I did something wrong. Not sure. Well, if you see something, let me know. This is the B port. B port goes to here. Not quite sure what's wrong. Strange, isn't it? Okay. If it took that display out, it seems okay. I don't know what happened. What went wrong? Oh, wait. No. The A's are okay. The B ones. Okay, let's put it here. And I want to display this. So far, so good. So far, so good. Now I want to connect this with this up here. Oh, now it works. I don't know why it didn't before. Looks identical. I just got rid of this and instantiated another one by copying. So if a component doesn't work, sometimes if you get rid of it and get another one, another identical one, it might work. Who knows what happened to that old one. So here we go. So let's try these out. Let's say, okay, let's save that. Say, how about 12? C, okay. And this, let's say 1. This, let's say 6. This, let's say 9. Okay, that works. And now the sum, what's the sum of that, right? So, well, let's get the sum out on a pin and then displayed hexadecimally, just like that. Oh, we haven't gotten the carry input yet, right? Let's get the carry input. I think we have to make this smaller. Whoops, sorry. Make this smaller. And then get the carry input. So that's the carry input, right? So why don't we route it this way? Okay, so carry input, data bit 1, so carry in, and I guess 24 points for that. Okay. All right. So now the output. Let's get an output pin. We want 16 bits. Make it real big. Okay. Make sure it has a connection nib there. So now we need a splitter, right? So splitter. Uh, faces north. Fan out is 4. Bit width and 16. So now conveniently, the least significant bits are to the right. That's good. If not, we would have to fix it. So we make that connection. Okay. So as you can see, we're getting an answer already, right? And you could do a binary addition to verify that answer. Oh, we need a carry out also. So that's from here, right? So let's so here's our carry out. So there you go. And now we're going to display the output in hexadecimal. So we can copy these ones. And if you don't see a circle when we mouse over a square, then oops, we didn't want to move this. No, we want to copy and paste. Oops, no. Copy, paste. And now this we have to be real careful about. We did it. Now the trouble is, let's see. Okay. All right. Let's see if we can wire You can wire that out this way. Oops. Oh, this got connected to all these, so that's no good. Let's try something different. Let's see. Okay. I think that works. Yep. And lastly, this thing. Okay. So let's see, this is like a sort of a random example, right? So does that plus that get you that? Well, let's see if we are any good at hexadecimal arithmetic, right? Let's save this file first. We have a carry out too, look at that. Okay. 9 plus 5 is 14, 14 is E, because 15 is F, so 14 is E. So that's correct, right? And a carry out of 1, right? 6 plus 6 is 12. Carry in of 1 is 13. 13, well, if 14 is E, 13 must be D, right? Sorry, that's wrong. 15 is F, 14 is E, 13 is D, 12 is C. So somehow 5, 5, 9, well, wait. 5, 9 is 14, which is E. 6, 6 is 12. Something is wrong because I'm getting a C here, which is 12, but it should have been a D, should have been a 13. So something is not working. That is, oh, here's what's wrong. What's wrong is in my head. Because the calculator is not wrong. It's what I thought is wrong. E is right. E is 14, but there is no carry out because this is hexadecimal. It is not decimal. So 14 is representable in 1 digit in hexadecimal. So there's no carry out. Got that? So there's no carry out. So and this is dark, which is correct. No carry out, right? You see that? So now we're in this unit. Maybe it's good to label these, right? Label so 0. You can't label in the center, so let's label it to east. And let's label that 1 to east. So let's label that 2 to the east, and let's label that 3 to the east as well. Okay. Okay. So unit 0 sends a carryout of 0 to unit 1 because E is representable in 1 digit in hexadecimal. So C is correct. 6 plus 6 is 12, which is C. Once again, there's no carryout from 1 to 2. And A plus 1 is B. We don't even have to know what A means, although it's 10. Plus 1 is B, which is 11. And carry out of 0 also. So D plus C, here's where there's a carry out of 1. So C plus D, well, C we know is 12 from that, right? So 12, D is 13, so 12 plus 13 is 25. 25 is more than 15. 25, what is 25 in hertz? So 25 is 16 plus 9, right? Therefore, 9 is what's represented, and then a carry out of 1. So this is correct. Now, for a little more fun, let's have a carry out here, right? Of 1 digit. Let's say, how about between this digit and that one? So the units, so 6, 6, 12 is not enough. Let's find something that adds to 16 or more, right? So 6 plus 6 plus 6 plus 10, let's say 16. 6 plus okay, 6 plus 10 is good enough. 10 is A, right? So instead of this, right? Let's make that A. What is that? That is B. That is the that is the 16th unit of B. So it's that unit of B, right? So you want to make that a 10, which is A, right? So one, sorry. So it's 10 is 1, 0, 1, 0. right? So okay, we got it. So now this is A, right? So 6 plus A is 0 with a carry out of 1, right? So you should get a 0, which you do, you get a 0 with a carry out of 1. See, light green, carry out of 1. Right? So a carry out of 1 plus A plus 1 should give you a C of carry out of 0. So that's correct too, right? So oh, that appears to work. And you should test a few more pairs of inputs, right? That will test different carry out units and so on. So any questions? So is there anyone who got anything to not work, or does everyone have something? Does everyone have everything working?
I can't get mine to work, but I think it started from the beginning, the full adder. So I'm just gonna rewatch your lecture from the beginning because I don't think I copied everything down right. I was late to class.
Oh, okay.
Um,
Well, you know, if we have some time, so you know, we can take a look at it if you want.
okay. And also I just screwed up my splitter. So I was trying to move it down and I accidentally deleted it and I was trying to make my connections back and I don't think I did it right. So I have a lot
Okay.
of cleaning up to do.
Well, if you want, okay. Well, if you want to try that, maybe um, your classmate or I might see what's wrong. So let's try that. Let's see. Let's down here. Who are you?
Zach.
Zach. Okay. Let's see if we can see your. Let's see. Oops. I saw you and now I don't. Let's see. Let's see. Let me. I'm still getting used to this. 1 second. I don't know what happened to your. But first of all, I'll undo. Oh, well, I guess. Why is that not showing? Oh, here. I'll make you a co-host. And now you can share your screen. Actually, I can remove the co-host. Oh, okay. That's right. Okay, all right.
So I don't know what I'm probably wrong in several different areas. Like I said, I was a little late. I was trying to catch up.
That- Okay. Okay, so that is your full adder. Do you get, why is that S in blue? Oh, it's, that S is not an output. It's not an output pin. You have to make it an output pin. Hmm?
Like that.
Yeah. Wonder why.
But
no,
before, when you were going through this, like, I don't know why this doesn't change. Like when I change these to 0 or to 1, it doesn't make a difference. And this
Yeah,
side,
something is funny about your, click on that S, go back to your selection tool. Go back to your selection tool. Up, left, up, left,
yeah,
way up, left corner.
okay.
Okay, yeah, click on that.
Okay, I see what
Okay.
you mean.
And click on your S, click on your output pin. Something is wrong with it. Does anyone see it?
The output is set to yes.
If I change it to no, then it changes it to whatever the square one is.
No, it should be output.
It should be a.
Oop.
Oh,
No, don't-
my bad.
Get rid of that. Get rid of that. Okay.
Yeah, I'm still learning how to use this.
No,
Oh,
that's
great.
fine.
I just got rid of everything.
Okay, that's all right. Put it back on. Maybe it'll work now.
Hey, I had the same issue earlier.
Let's see where.
If I hit the simulate button up in the top and then do simulate enable, if I
Okay.
toggled that, it sometimes fixed it.
Oh, okay. Yeah. Oh, okay. Okay, it looks like it fixed it. Yeah, you're right. Thank you. So yeah, it looks like it's done. So now save the file. Oh, this the label it S. Yeah. Okay. Okay. Make it a little bigger. That S.
Oh, yes. Is that good?
Okay, save the file. Now let's look at your 4-bit.
To add 4.
Okay. Something is wrong with your output. That red there.
Right. I don't. That wasn't there before. I don't know what I did. I think there's something wrong completely in my full adder because when I click when you had all yours lit up, wasn't this one lit up as well? This
Oh, well, okay. But I think that that exclusive OR wasn't right. Isn't right. So why don't you go back to the selection tool again? Click on the exclusive OR. It's the multiple input behavior that's not right. Go down.
that one?
Yes, that one. It should be the other one.
Like that.
Yeah.
Okay. But then should both of these be red?
So now, now you're supposed to test if this is right, but let's go on. You can do that at home. Let's go on to that. Yeah. Okay, you still have that same red. why don't you just remove those red lines? Or that one, yeah. Okay, now that's not red anymore. So let's show the whole thing bigger. Okay, now let's connect that. Connect that
This-
line again, yeah. Oh, something is still wrong.
Is the output setting wrong again? 'Cause it's a block when it should be a rounded.
Yeah, you're right. Maybe that's what it is.
This one.
No, well, that too. Yeah, both of them. They should be output.
But okay, and this one should be output as well.
Oh, yeah. Because it is.
Okay.
Okay. Now it appears to work, right? So you have to test it still. So so save that, save the file.
Okay.
Save the file and go on to the add 16, right?
Yeah. So I had a splitter down here like you
Okay.
did, but I was trying to move it down and I accidentally deleted it. So I just haven't connected everything back.
Okay. Okay.
I think I can do that on my own though, and it should all probably
Okay.
work out now.
All right. All right. That's fine. Yeah. That's
Thank you.
okay. Anyone else? Well, seems like that's it then. That's good. It appears we got everything working. So you just have to go home, write it up, test each stage out in detail. I was going to show you. Going to show you a counter as well, which you could use to test things. Maybe I should do that. We have a few minutes left. Maybe we can do that, right? So that's a nice thing to use when you need to test something. Let's see. I gotta share my window again. Oh, I think you have to unshare. Wait, oh. I guess I am sharing. Okay. Okay. So add a new circuit. Now, in real life, sometimes you can have a circuit that tests another circuit, right? So we can do that in simulation as well, right? I want to test the full adder by using a counter. A counter is a circuit that has memory, and it counts up 0, 1, 2, 3, 4, 5 like this to the maximum value, and it falls down to 0 again. So I can name a circuit like a full adder test. Okay, that will test my full adder, and I just instantiate a full adder. Like that. Okay. And that side is the input side, right? I have that's my C in A and B, and then S and cout. So what I want to do is I want to instantiate a counter. So under memory, I'm going to get a counter, okay? And with this counter, I want to be able to count from 0 through 7, okay? Because my inputs go from 0 through 7, right? So data bit is actually just 3 bits, okay? So the maximum value is 7, right? An action on overflow is wraparound, which is right. The trigger is the rising edge. Okay, well, a circuit with memory usually has a clock. If it's, well, there are 2 kinds of circuits with memory: asynchronous and synchronous. We'll only deal with synchronous circuits, even though I've done research on asynchronous circuits. But for this class, we'll just look at synchronous circuits because they're easier and they're more prevalent, ubiquitous, pretty much. So, so let's do that. So the trigger is the rising edge. Well, there's a clock that drives the circuit. The clock is basically a square wave, okay? But we're going to use a button to generate the clock. Right? So here's our circuit. That there is your output, okay? Now, down there is your clock, okay? And there are some outputs here, but we may not need them. Basically, here, in the input output, there's a button which we'll use. Okay, a button is something where it's normally 0, but if we click on it, it's like pressing a button. It will go to 1, and if we unclick it, it'll go back to 0. Okay, so then notice this. I'm getting this hand symbol again. If you click this, okay, notice this number. Each time I click on it, as it goes from 0 to 1, it will increment that number. 1, 2, 3, 4, 5, 6, 7, back to 0. Okay, so we're going to use that as a as an excitation signal for our counter. Okay. So now this this thing that comes out here is 3 wires, right? That goes 0, 1, 2, 3, 4, 5, 6, 7. So we have to use our splitter again, right? So we get a splitter under wiring, right? Splitter. Right. So we want the splitter to face east, okay? And the bit width in is 3, and the fan out is also 3, okay? So as you can see, the fan out is 3 like this. Okay, so now we connect the input to that splitter to the cube, right? And so if you, without making the connection, if we click on the switch repeatedly, note that will count up. Remember, dark green is 0, light green is 1. So 1, 2, 3, 4, 5, 6, 7. See? And down to 0 again. So if we make that connection, Oh, sorry. Can you make that connection? Okay. That will actually, these 3 lines will be the inputs that our adder needs. Okay. And now we will take these outputs. Let's see, that one is C out. So that one will be the more significant digit, and that's the sum. That will be the less significant digit, right? So we'll take that and this to different LEDs. Facing south. So that will be an LED, right? Okay. So that will be the ones and that will be the twos, right? So this, as we click on that, right, that should count that should count the 0 through 7, right? And that should be going through the different rows of the truth table, and that should be your output, right? So when this counts 0, the 0, 0, 0, that should come out double 0 as it does. When this counts 1, okay, that should be outputting 0, 1, right? When it counts 2, that should be 0, 1 as well, because when the input line is 0, 0, 1 or 0, 1, 0, the output should be 0, 1, right? So let's try that. So, okay, that's 0. So that's 0, 0. That's correct. This is 1, 0, 1. That's correct, right? When that says 2, this should be the same, 0, 1, right? There's 2 in the input means you have 0 and 1 and 0 in the input. So in the output, it says 0, 1. And you have 0, 1, 1. This should be 1, 0 now. That's correct, right? So you go, that is 4, right? 4 in the input means the output should be 0, 1 as well. 5, you should get 1, 0. 6, you should get 1, 0. Now, all ones, you should get 1, 1. So that operates correctly, in other words. Okay? So this is a circuit for testing the full adder. Counter. Any questions? So this is basically your test bench, if you like. This is called the test bench. Any questions? Okay, we're done.
Hey, actually, I've got one. Could you
Oh,
click
yeah,
on the
sure.
splitter for a second? Mine's not functioning. I
Oh,
wanted
okay.
to see your settings.
This splitter right here?
Yes.
Okay. There it is. So facing east, fan out of 3, bit width in 3.
Yeah, mine matches. It's just not working for some reason.
If you click on that and just kind of move it around a little, see what happens.
Okay, yeah, I'll try that.
Yeah.
Yeah, I've got something weird still going on, but
Okay.
I can work on that.
Okay, okay, all right. And you can email me. If you email me and I don't see it, you can put, I don't know, exclamation points or something on the subject line. Sometimes I'm busy and just don't see things coming in. So,
Okay. Which adder did you use that splitter is feeding?
the full adder, the one we designed.
Okay. All right. Thank you.
Yep. Any more questions? Well, we are done then. That's great. So I made the due date for this a few days after. I still have to figure out what to do for people who didn't finish the fourth part. Is there anything but the fourth part that's not finished? So it's basically the fourth part. So I have to think up something to do, in place of that. So I'll let you know really soon. If there's not enough time to do the rest of the report and leave that open, and then I'll figure out something to do in the next few days. Maybe an essay or some kind of problem to solve or something you could simulate. I don't know. Let's see. There's one person who have your own equipment at home. You can use that and see what happens. The oscilloscope has to be fast enough. If it's really old or not fast enough, then you may not get a delay that makes sense. In which case, we'll figure out something. Okay. See you next week. I don't know yet what mode it's going to be, but I'll keep you posted. Okay, I guess that's it.
Thank you, Professor.
Oh, you're welcome.